I have more to say about that. Small b, sorry. Sorry, for small b, fixed p for small b. Sorry, sir. I just said the opposite. Okay, so for the purpose of estimation, since the questions in the survey are in average how much money do you have, what I want to do is I want to compute. So I give you M star. M star is really the only decision. Given M star, you know the decisions. Now this part is accounting, in a sense. Given M star and the value of P and the value for pi for inflation, I could figure out how much money you have in average. I could figure out how many withdrawals you make, and I could figure out how much money you have at the time of the withdrawal. These are precisely the variables that are asked in the survey. That's why I want to figure them out, because I want to estimate the model. So notice, for instance, the withdrawals, there are two types of withdrawals. And I forgot, there's one more variable of interest, which is the number of trips, which is also a function of M star. So you do more than P trips. You do P, which are the trips that you do because they're free, plus a little bit more, because sometimes you hit zero. How often you hit zero depends how much you consume relative to how much money you take off. It's sort of natural to expect this formula. It just comes from the fundamental renewal theorem. But whatever, it's just weird. If you think it through, it's kind of what you should expect. But you need to think it through like half an hour, so we're not going to do it. So, but the point is that N is the number of withdrawals, P is the one that you do just by chance, the ones that you were stranded in the airport. So there are two types of withdrawals. These ones are kind of Baumol-Tobin type of withdrawals. You withdraw the whole amount, and this one you withdraw just the difference between your target and what you have. So you can, by the way, the invariant distribution of cash holding, for which you are taking this expectation with respect to, it has an ODE that is there, it has a simple solution. So you're ready to estimate this model, but before that, I'll make one point. This parameter, B hat, is the same one as in the steady state model, and that's why I put it there. It turned out to be that the whole shape of this model, even in this version, is just a function of this simple parameter. Notice what this says. If you look at the statistics that we're going to measure in the data, W over M, or M low over N, or N, the number of withdrawals, they are a function of B hat over R. And as B hat goes between the two limits, 0 and infinity, you either have Baumol-Tobin, which W over M is 2, M low over M is 0, and the elasticities, all of them are equal to 1/2. Or you could go, if you want, to the other extreme, in which all the elasticities are kind of 0. W over M actually goes to 0, kind of extreme, and M over bar over M goes to 1. So you could span the whole spectrum of all this behavior, but it's a one-dimensional. Okay, so that's for So for those of you that think about econometrics, that's going to get the identification, because you're going to have multiple observations. So let's just talk about identification. That's what this picture is for. So the idea is that you're going to have, for a given household, you could estimate the model. Why? Because you have a bunch of different decisions: how often to go to the bank, how much money you withdraw on average, how much you have at the time of a withdrawal, all related to essentially two parameters. So that's going to give you over-identification. So you're going to be able to, if you want, you could estimate the model with one single observation for each household. But remember, one single observation has questions about a bunch of stuff. Okay, so the theory is simple, has few parameters and a lot of predictions, and we measure a lot of predictions. So we get kind of identification. That's the whole idea. And that's why I don't have to care so much about the other shocks and the other stuff, because what is a typical money demand estimation, or a typical whatever estimation? You have a model, you have one variable that moves, a bunch of other unobservables. You hope that all the other unobservables are uncorrelated to whatever variable you observe, like an interest rate, and then you use OLS. And then you start saying then an instrumental back and forth or whatever, use 10 years before the data or something. But the point here is that if you actually use a theory, there's a combination of having a theory with very few parameters and the data is very rich. So in some sense, it should be very easy to reject the model. But that's another way of saying that it's over-identified. So I'm going to show you some data. By the way, one more thing. Notice that what this is a functional noise is beta over r, not just beta hat. For technological changes, beta hat has information, it has a p, actually p squared. But suppose that you keep beta hat fixed and you move r. This is like the other model. As you move r, the elasticities, so you move r down, let's say you go to interest rate close to 0, then you're going actually to this case, in which all the elasticities are equal to 0. That's like a simple Bauman-Tobin model where you have these two different regimes. By the way, this is kind of like a liquidity trap. The money demand, the elasticity getting to 0 when the interest rate is getting to 0. I mentioned this because this is something also that now we see in the data, not only in terms of the interest rate being very low and the money demand being very inelastic. That's the whole point of not having hard time to sort of change interest rates and changing liquidity. And that's why I show you this aggregate data to motivate that the consistency between kind of household level data and aggregates. Okay. So now let's back to this and to the estimation. Okay, I don't have much time, so there's some other versions with some other shocks, which I'll skip. And maybe what should I do? So essentially there are two parameters to estimate, these two. P and this parameter. Now it is true, we have observations of C and we have observations of R, and hence, if we estimate this number, then we could divide by the product of C times R and obtain D. But really what the model, the predictions of the models are, given P and B over C over R, it gives us predictions for all these variables, which we measure in the data. So the thought experiment is that I take a household, say I take Benny, and I ask Benny, tell me what is your M over C, W over N, N and M lower bar over N. These are four numbers. They are functions of two fundamental parameters. So if the model is correct, basically I have sort of 2 degrees of freedom. Then I could go to Valentin and that's the same, right? Now we're not going to do exactly that. We're going to append measurement error to each of the variables, and then estimate the model at maximum likelihood. So I'll tell you why we use measurement, why we think that it's reasonable to use measurement error. Well, it's typically a lot of measurement error in surveys, but this one is kind of fun to see. Well, I don't know, to me.